What is this? It's a strange container. If we measure the amount of water with this, it might give strange results. It's a mystery. By the way, who invited us to this laboratory? It looks like no one is here.
Zundamon, look at that. There is a note from a missing researcher.
Missing? What happened here? With this container, you can multiply using water. That's what it says. Multiply using water? What does that even mean?
As it is, it's hard to understand. First, let's try an experiment using normal containers. I'll prepare 2 normal containers here.
Yeah, they look like normal shakes.
Let's fill the left container up to 3. And fill the right container up to 2. Finally, if we pour the water from the right container into the left container, it becomes like this.
The answer is 5. In other words, we have calculated 3 plus 2.
Exactly. Since we added water, it corresponds to addition. Up to here, it seems obvious. Now what about this container?
It's that strangely shaped container from before.
As a side note, this container is flat, so its thickness is constant.
Got it.
Now, let's prepare 2 of these containers. As before, fill the left container up to 3, and the right one up to 2. Finally, if we pour the water from the right container into the left one, it becomes like this.
The answer is 6. In other words, we calculated 3 times 2.
It seems so. When we add water in this container, it somehow corresponds to multiplication.
Isn't this just a coincidence? We just added water. There's no way we could be multiplying.
Wait a moment, Zundamon. The shape of these containers, doesn't it look familiar?
Huh? I've never seen a shape like this.
Then, what if we do this?
Oh, this is a graph of inverse proportion.
Good memory. When x and y satisfy the relation y equals a over x, we say y is inversely proportional to x. Here, a is a non-zero constant. This graph assumes a is positive. As x increases, y decreases. More precisely, as x moves away from 0, y approaches 0.
It's exactly the opposite of proportion. That's inverse proportion. Mysterious containers that allow multiplication with water, and they have the shape of an inverse proportion graph. The mystery only deepens. There must be some important relationship between multiplication and inverse proportion. But I don't really understand what that relationship is. How can we solve this mystery?
I see. First, let's interpret the earlier experiment using graphs of inverse proportion. Here, water was stored in 2 containers. And when we rotate them,
they become graphs of inverse proportion.
By interpreting them as graphs like this, we can proceed mathematically. Now, to simplify the calculation, let's set the constant of proportionality to 1.
Understood. So, this container is flat, and its thickness is constant. That means the amount of water is represented by the area between the graph and the x-axis.
Exactly. Here, the range in the x direction starts from 1 in both cases. In the upper graph, water is filled up to 3. Let's call this area S of 3. Similarly, on the lower graph, water is filled up to 2, so we call this area S of 2.
Now we want to add the water in the 2 containers. How can we represent this using graphs?
This part is a bit tricky. What we're trying to do is pour S of 2 into S of 3. However, simply attaching the 2 shapes doesn't help much. So first, let's transform the lower shape while keeping the area S of 2 unchanged.
I see. This way, we can attach S of 2 to S of 3. Combining them gives the area up to 6, so we can express it as S of 6.
Yes. Combining S of 3 and S of 2 gives S of 6, which means we have calculated 3 times 2 equals 6.
Wait a second. I feel like we're missing something. We transformed the shape like this, while keeping the area S of 2 the same. Does the endpoint really become 6? If we don't prove the endpoint is 6, we can't say we calculated 3 times 2.
I didn't mention it on purpose, but I'm glad you noticed it yourself.
What?
Indeed, we need to prove the endpoint becomes 6. Alternatively, we can prove that the two areas are equal when the endpoint is 6. However, proceeding like this lacks generality, because we can only calculate 3 times 2 this way. We need to generalize the situation. As preparation, I want you to notice something. Each x-coordinate is multiplied by 3.
X-coordinates, you mean these? Indeed, 1 becomes 3, and 2 becomes 6.
That's correct. Now we're ready. Let's generalize the situation. Let the range in the x direction be from 1 to b, and define the area of this shape as S of b. Now multiply the x-coordinates by a, so the starting point 1 becomes a. Next, multiply the endpoint b by a to get ab. In short, we consider this transformation. We want to prove that the area remains S of b after this transformation. As shown in the figure, assume that a and b are greater than 1.
I see. This should correspond to multiplication of a and b. In other words, we just need to prove these two areas are equal. That sounds easy. So, how do we prove it?
Well, it's difficult to prove this directly. So instead of proving the areas directly, let's draw rectangles around each shape and prove that the rectangles have equal areas.
I think we can prove it. First, let's calculate the area of the left rectangle. The width of the rectangle is b minus 1. Let's call this w sub 1. Next, the height is... How do we calculate it again?
This curve is the graph of y equals 1 over x.
Right. So when x is 1, y is 1 over 1, which is 1.
Exactly.
Therefore, the area of the left rectangle is width w sub 1 times height h sub 1, which equals b minus 1.
Well done!
Next, let's calculate the area of the right rectangle. The width is ab minus a, and the height is 1 over a.
Same idea as before.
Yes. So the area of the right rectangle is width w sub 2 times height h sub 2, which equals b minus 1.
The results match.
Oh, you're right. What's going on here?
It's easier to understand this way. Comparing the two rectangles, if you multiply the width of the left by a, you get the width of the right. Next, if you divide the height of the left by a, you get the height of the right. So the width is multiplied by a, and the height is divided by a.
I see. When transforming the rectangle, the length in the x direction is multiplied by a, and the length in the y direction is divided by a. That's why the area does not change.
It seems you understand. Up to this point, we've been considering the areas of rectangles, but the same can be said for the areas under the inverse proportion graphs.
The x direction is multiplied by a, and the y direction is divided by a. Therefore, the two areas are equal.
Just to be safe, let's confirm one thing. Do the two shapes really overlap perfectly after this transformation?
Now that you mention it, I'm getting worried.
Okay. First, choose any point on the graph in the left interval. If the x-coordinate is x, then the y-coordinate is 1 over x. Next, multiply the x-coordinate by a. It becomes ax. Finally, divide the y-coordinate by a. Then it becomes 1 over ax.
Oh, I see. The initial and final coordinates just replace x with ax, and both are expressed in the same form. So both lie on the graph of the inverse proportion.
This confirms that the two shapes perfectly overlap after the transformation.
Let's sum up. The left container is filled up to A, and the right container is filled up to B. Representing this using inverse proportion graphs. It becomes like this. Then we transform the graph for B, multiplying the x direction by A and dividing the y direction by A. This transformation preserves the area. And when we combine S of A and S of B, we get S of AB. because the right endpoint becomes AB. So by adding water, we effectively perform multiplication of A and B. We can express this with an equation like this.
Here, addition of areas corresponds to multiplication in the x direction. We can now see a fascinating relationship between addition and multiplication. We can take this understanding one step further.
Really?
S of AB represents the area from 1 to AB. Moving from 1 to AB can be interpreted as multiplying 1 by AB.
Well, that's true.
Now let's break the operation of multiplying by AB into two steps. First, multiply 1 by A. Then, multiply by B. This gives the result AB.
Whether we multiply by AB at once, or multiply by A and then by B, it feels obvious though.
Look carefully. Here, multiplying by A corresponds to the area S of A. Similarly, multiplying by B corresponds to the area S of B. Here S of B equals the area from A to AB, but it does not depend on A. It corresponds purely to the operation of multiplying by B.
Oh, I see. So this equation means, whether we multiply by AB at once, or multiply by A and then by B, we reach the same result in both cases.
Yes, that's a good interpretation. By the way, this equation, doesn't it look familiar?
Wait, really?
On the left side we have multiplication, and on the right side we have addition. In other words, multiplication becomes addition.
I think I've seen this before. Could it be logarithms?
Yes. From here, it gets a bit more advanced.
Now I'm getting nervous.
S, which represents the area under the inverse proportion graph, can be seen as a function. This function converts multiplication into addition. This is exactly the property of logarithms. Logarithms also turn multiplication into addition. And it's not just that they share the same property. In fact, S is the logarithm itself.
What?
So far, we defined S as the area under the inverse proportion graph.
We represented the area from 1 to x as S of x.
If the constant of proportionality is 1, this area equals the natural logarithm of x. A natural logarithm is a logarithm with base e, Euler's number. Here we write the natural logarithm of x as ln x.
So the natural log of x equals the area from 1 to x. That's kind of amazing.
We can express this using an integral like this.
Wow, that looks complicated.
It looks hard, but it's simple. It says we integrate the inverse proportion function from 1 to x. This corresponds exactly to this area.
I see.
Now what happens if we differentiate the natural log of x?
What happens?
Here's a hint. Roughly speaking, differentiation and integration in one variable are inverse operations.
Okay. Differentiating the natural log of x means differentiating this integral. So we integrate the inverse proportion function and then differentiate it, which gives back the same function.
A nice and simple result. This derivative formula of a natural logarithm is well known, so some of you may already be convinced.
Maybe.
This formula is simple, but also quite mysterious. I hope this video has given one way to understand it.
That sounds like something the creator of the video would say.
By the way, in this video we explain another interpretation of this formula. There is a link in the description, so please check it if you're interested. However, it is quite advanced, so please be careful.
Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.